Okay, so this video is going to start talking about the problem-solving process. Okay, to me, the first step in problem-solving is always the draw step. And so what we're going to do is we're going to learn how to draw free body diagrams. Okay, so when looking at problems that involve forces, it is best, or it is almost required. Oh, sorry about the yellow. Erase that. We'll get a red in here. So it is almost required to draw a free body diagram. Okay. We call them FBD for short. Okay. Now, what it does is it just helps you visualize what forces are acting on the object and the directions they are. Okay. All those forces that we talked about with the contact versus field forces video. Okay. They all point in specific directions. Okay. Some point vertically, some point horizontally. Some can point in horizontal one example or one problem, but then vertically in another problem. So you just need to make sure you're doing a good job of kind of identifying what forces are acting in what directions. Okay. So here are the steps to drawing a free body diagram, or an FBD. Okay. Step one: identify the forces that are acting on the object. Okay. Now, what helps sometimes if you're just getting used to doing free body diagrams, it may be helpful to write them down and then kind of organize a little bit of a chart, like, you know, that one's going in the horizontal and one's going in the vertical direction. But that just may be helpful. As you gain experience, you don't typically write them down, okay? As you get more comfortable with the free body diagrams, you don't write them down, you just go for it, okay? So you're gonna indicate your coordinate system, okay? Or coordinate axes, okay? Oh, I missed the word system. Okay. Now, what happens is the coordinate system helps us identify positive. Right. So in our coordinate system, we're going to identify which direction is positive x, which direction is positive y. Okay. So any force that acts in the negative direction, okay, and that doesn't follow our coordinate system, that's going to act in the negative direction. Now, what happens, and this is where math teachers don't like physics teachers. Math teachers just like to keep their coordinate system as is, right? Keep it positive x to the right, positive y up. Now with physics, we can turn, or we can change our coordinate system, our coordinate axes, to make the problem easier to solve. One example would be inclined planes. Okay, if we keep it traditional, in the sense that we'll keep, you know, positive x to the right, positive y up, our problem becomes a lot much harder. Okay, it doesn't necessarily become harder, it just adds in more trick. Okay, but if we turn that axis to either go up the incline or down the incline, or, you know, basically to follow the incline, now we only have one force that is at an angle, and that's what we want. Okay, and so another thing would be when we do connected object problems, you may end up with a positive x pointing down and a positive y pointing to the right in some situations, and as we go, we'll identify why you need to do that. All right. So step 3, you're going to draw one of two things. You're either going to draw a box or a dot. Okay. The box, if you're talking about an object, like specifically, like, you know, a crate on the floor, a car on the road. Okay. All right. And a dot, if you're more talking about, you know, a point of interaction. Okay. A POI. Right. So dots are typically when you have like tension problems. Okay. So if I got all the ropes meeting at one point, okay, I'm going to draw a dot for that point. Okay. Now what you can do on the box or dot, you're going to draw arrows. Okay. That represent the forces you kind of identified in step 1. Right. So you're going to draw arrows and making sure to label them. Right, just don't draw the arrow, make sure you label them. Okay, they should be relative in size. So for example, here in step 5, do not draw this on the box or dot, but you want to identify the object's acceleration if possible, or if it is accelerating. Okay, and this is going to help with finishing, you know, the problem, because drawing the free body diagram is just one of the steps, okay, in doing Newton's second law problem, or Newton's law problem, okay? So here are just some examples, okay? So I got a book sitting on a table, right? So what potential forces do I have acting, right? H, V. Well, I have nothing in the horizontal, right? Because it's just sitting on the table. In the vertical, I have the support force, which we know is a normal force, and then I have the weight. Okay, so now how do I draw that on my... Now, another thing you can do when writing them down, you can indicate which way they're acting. Well, this is going to act positive because the table is going to push up on it. I'm sorry, I want to erase that. My box is kind of in the way. Okay, and we always know that the weight is always going to act straight down. Okay, and so now I draw the box, and now I can draw the arrows. And these two should be relative in size, right? About the same size because they are balancing each other out. Okay, so I've got my Fn up, I have my Fg down, off to the side. If we're just sitting on a table, we're not accelerating. Okay, notice I didn't draw that on the box. Okay. All right, next one, a book sliding with a constant velocity on a frictionless table. Okay, one thing to note here, there is no applied force, right? So at some point in time after you apply the force, okay, so I have my little, let me identify them. So I have no horizontal forces, and so I have the table support force up, I have the weight down, okay, and so now here's my book. Right? And so I have Fn up, Fg down, and because it tells me constant velocity, I have no acceleration. Okay? Now, you can't, it's kind of weird because A and B have the same free body diagram, but A is not moving, B is moving. Okay? You don't indicate motion on the free body diagram. Okay? But you would indicate acceleration if it did exist. Okay. All right. Part C, or example C, a book being accelerated to the right by an applied force on a frictionless table. Okay. So here's my forces. I have an applied force, and it says to the right, so it's going to be positive. Right. Oh, I forgot. I didn't identify coordinate system. Sorry. Positive, positive. Right. Positive, positive. Here we go. Positive, positive. Okay. And now we've got our normal force because we're on a table, and then we have our weight, right? Because it's balancing the normal force. And so here's my box or my book, or right? And so now I draw my arrows. Fn, Fg is my vertical side. And now I have this applied force. Right, and it's telling me in the problem that I'm accelerating to the right. Okay, so that was what it would look like there. Oh, let me pan up a little bit. Okay, a book sliding to a stop on a table with friction. So what this is telling us is that we've exerted a force, we've pushed it, it's accelerated, but now we're not applying another force after that, and so it's just coming to a stop. So since we're on a table, we have our Fn, we have our Fg, okay? And now we have friction, and to get this to stop, the friction would have to apply in the negative direction, okay? So here's our coordinate system, positive, positive, okay? Now we do our box, right? So this is our book. And so now I do my Fn and Fg, right, my verticals. These, again, will still be kind of relative in size, right? Same size because we're not doing anything different, okay? And now the friction will be in the opposite direction, right? So I do want to indicate, like, motion is to the right, right? So if it's going to the right, the way the friction has to apply, or the acceleration would have to be opposite the motion, okay? Again, notice I'm not drawing my acceleration vector on my diagram. Okay, and we'll get into that when we talk about the test-taking strategies for the test. Okay, an object in free fall. Okay, so remember, we talked about free fall, the object is falling, so there's no horizontal, and the only force acting is Fg, right? And so here's a positive, positive. So no, there's no surface, so there's no normal force. Okay, and we're talking about in free fall, which we say no air resistance, right? So no air resistance. Okay, so that's why we don't have anything but Fg there. Right, so here's our object, Fg, right? The force of gravity, and our acceleration would be directed downward. Okay. All right. Now the next one, an object that has reached its terminal velocity. Now terminal velocity is a special point. Okay. Again, since we're falling down, we have no vertical forces, so we have our Fg, which would be negative, but when we talk terminal velocity, that means now we have air resistance, right? If you take physics C, we'll get into that. So we'll call it F air, right? And it's actually just a special type of friction. And I failed to mention in the contact versus field forces video, friction always opposes motion, right? So air resistance is a special type of friction. So if the object is falling down, air resistance acts up, okay? And so we have F air, and then we have Fg. And now because these are, right, it's not quite relative, but because these are balanced out and they tell us constant velocity, our acceleration is 0. Right? So there are just some simple examples as to free body diagrams. And the reason why we have to do free body diagrams, because this starts the process, right? This starts the problem solving process. Okay, and AP is broken apart problem solving away from first and third law. So this actually ends unit 2.1, and we'll start diving into unit 2.2 with the problem solving in the next set of videos.